In their mission to figure out the first stars and galaxies that illuminated the universe, space experts are still in obscurity. However, they are drawing nearer to enlightenment one revelation at a time. That is the amazing inevitable end from extraordinary revelations by the James Webb Space Telescope, or JWST, the $1 billion time machine that just formally completed its most memorable year of observations. Designed to impression the weak infrared glow of the universe's earliest brilliant objects, Webb's vision ventured back into the first 100 million years after the Big Bang, allowing it to acquire more and better information about infant systems than any other facility yet assembled. However, its haul of cosmic baby pictures has proven more plentiful than most analysts dared to hope. Simply put, candidate galaxies in the early universe are appearing in numbers that challenge predictions, with dozens observed so far. This makes researchers excited, as Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We, truth be told, weren't anticipating this." In the weeks and months following JWST's discoveries of surprisingly mature early worlds, scholars and observers scrambled to make sense of them. Could the flock of odd, enormous, and bright early galaxies be an illusion, perhaps due to flaws in the analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models, or might they be the first clues that the universe is more strange and complex than even our boldest hypotheses had ever assumed? Was the Big Bang Theory wrong? Join us today as we delve deeply into how the James Webb Space Telescope revolutionized our understanding of the universe. To comprehend the difficulty, we must return to when the universe was believed to have been formed after the Big Bang. The baby universe began cooling, and within a few million years, the roaring plasma that filled space settled down. Electrons, protons, and neutrons combined into atoms, mostly neutral hydrogen. Things were calm and dark for a period of uncertain length known as the Big Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see called dark matter. It exerted a strong influence over the universe, particularly at first. In the standard picture, cold dark matter, a term that implies invisible or slow-moving particles, was flung about the universe indiscriminately. In some areas, its distribution was denser, and in these regions it began falling into clusters. Visible matter, meaning atoms, clustered around the bunches of dark matter. As the atoms cooled, they eventually condensed, and the first stars were born. These new sources of radiation reionized the neutral hydrogen that filled the universe during the so-called Age of Reionization. Through gravity, larger and more complex structures evolved, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe is expanding rapidly. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Consider the universe as a loaf of raisin bread. It starts as a mixture of flour and water, yeast and raisins. When you combine these ingredients, the yeast begins to breathe, and the loaf starts to rise. The raisins inside it represent galaxies, extending further apart from one another as the loaf expands. The Hubble telescope observed that the loaf is rising even faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the shocking energy of space itself, called dark energy, which is represented by the Greek letter lambda. Plug values for cold dark matter, standard matter, and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter, lambda CDM model matches almost all observations of the universe. One way to test this model is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the Big Bang. The universe was simpler then, and its evolution is easier to compare against expectations. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of a void-looking patch of space in the Big Dipper. Astronomers were astounded by the abundance hiding in the inky darkness. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone expected. Hubble went on to discover some truly distant galaxies. In 2016, Astronomers found its most distant one, called GNZ11, a faint smear dated to around 400 million years after the Big Bang. This was surprisingly early for a galaxy, but it didn't stand out in the lambda CDM model, partly because the galaxy is small with only 1% of the Milky Way's mass, and partly because it stood alone. Astronomers needed a more powerful telescope to see whether GNZ11 was an outlier or part of a larger population of surprising early galaxies, which could help determine if we are missing a fundamental piece of the lambda CDM recipe. That's why the James Webb Space Telescope, or JWST, was conceived. Known as the largest and most powerful observatory ever launched from Earth, JWST was built to revolutionize our understanding of the universe. Positioned 1.5 million kilometers away from Earth's interference and cooled near absolute E0 by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and incredibly sensitive instruments designed to reveal details of cosmic dawn never before observed. And that promise was kept. The first discoveries were received within just weeks of JWST's full operations, beyond cosmologists' wildest dreams. It has seen galaxies astonishingly close to the beginning of recorded history, examined the atmospheres of exoplanets in remarkable detail, and provided stunning new views of worlds in our solar system. But it's just getting started. As Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to acquire more and better data about infant galaxies than any other facility yet built, the question is nothing less than our very understanding of how the structured universe we know emerged from primordial chaos. JWST's early discoveries could rewrite the opening chapters of cosmic history, which concern not only ages and faraway galaxies but also our own existence here in the Milky Way. As JWST scientist Mark McCaffrian, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm but to break it. You just don't know how they will break." Researchers use a version of the Doppler effect to measure the distances of objects. This is similar to figuring out the location of an ambulance based on its siren. The siren sounds higher in pitch as it approaches and then lower as it recedes. The farther away a galaxy is, the faster it moves away from us, as its light stretches to longer wavelengths and appears redder. The size of this redshift is expressed as z, where a given value of z tells you how long an object's light had to travel to reach us. One of the first papers on JWST data came from Naidu, the MIT cosmologist, and his associates, whose search algorithm flagged a galaxy that appeared mysteriously bright and impossibly far away. Naidu named it Glass Z13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was renamed Glass Z12. Other cosmologists working on different sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called CRS 1749 or CR2Z71, whose light appears to have left 13.7 billion years ago, only 220 million years after the Big Bang, barely a blink of an eye after the beginning of cosmic time itself. These putative detections suggested that the perfect story known as lambda CDM might be incomplete in some way. Galaxies grew enormous immediately in the early universe. "You don't expect to see massive galaxies," said Chris Lovell, an astrophysicist at the University of Portsmouth in Britain. Indeed, in a study published in November, researchers investigated virtual simulations of galaxies governed by the lambda CDM model and found that JWST's early bright galaxies were an order of magnitude heavier than the ones that formed at the same time in the simulations. Some astronomers and media outlets claimed that JWST was breaking cosmology, but not everyone was convinced. One issue is that lambda CDM predictions aren't always clear-cut. While dark matter and dark energy are fundamental, visible matter has complex interactions and behaviors, and nobody knows exactly what happened in the first years after the Big Bang. Those frantic early times must be approximated in computer simulations. The other issue is that it's hard to tell exactly how far away galaxies really are. In the months since the first papers, the ages of some of the claimed high redshift galaxies have been revised. Some were downgraded to later stages of cosmic development due to updated telescope calibrations. CRS 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago. Naidu says it's possible the galaxy is part of this cluster, a closer interloper that might be filled with dust, causing it to appear more redshifted than it really is. According to Naidu, Source 1749 is unusual regardless of how far away it is. It would be a new type of galaxy that we didn't know about, a very low-mass, tiny galaxy that somehow accumulated a lot of dust in it, which is something we generally don't expect for very far-off galaxies. Everyone knew that the most conclusive,